Hello, I'm going to present you a low-cost architecture for monitoring a greenhouse. My name is Francisco Javier Ruiz Ortega, doctorate student of the Tecnológico Nacional de México, CENIDED. Worldwide agricultural activity faces the challenge of ensuring the supply of food to the population. Therefore, the adaptation of technologies is an optimized to optimize the production units more than to enable new growing lands. Current farmers are adopting emerging technologies to better manage the controls of the elements involved in the productive process: climate, pest, disease, nutrients, and water supply, incorporating each time more technologies such as the Internet of Things, computing in the cloud, computing in the fog, integrated systems, sensor, wireless artificial intelligence, and monitoring and predictive systems. These There are several works that use technologies from the Internet of Things with promising results. However, despite these results, the implementation of the so-called intelligent agriculture is difficult to implement due to the expensive access to the small products and difficult equipment, in addition to the difficulty of connection to the Internet. Proposed IoT architecture. In this section, we present our proposed architecture for the automatic monitoring of the greenhouses. The architecture is made up of 4 layers: the perception layer, the network layer, the storage layer, and the application and business layer. Perception cloak. The detection layers allows you to collect context data inside and outside the greenhouse. The first step in this layer is programming the Arduino microcontroller. These sensors integrated into the Arduino board were air temperature sensors, related humidity sensors, soil humidity sensors, wind speed, solar radiation, infrared plant temperature sensors, and light intensity sensors. Network layer. The network layer establishes the connection negotiations between the ESP8266 module and the local network in order to send the data collected via Wi-Fi to a web server. This layer is responsible for sending the ESP8266 module is used as a bridge between the Arduino Mega microcontroller and the web server. However, it has the capability to run standalone applications. The ESP8266 model can work as a server or as a client. In this case, it was configured to work as a client to connect to a web server and be able to send data. The storage layer. The storage layer is located on a cloud web server which has support for server-side programming language, PHP, and a MySQL database manager. For the storage of the data coming from the network layer, a MySQL database with a table was developed. Also, a web service program with the PHP programming language was implemented, which receives the data sent by the network layer, makes the connection to the database, and inserts the data in a table. Application and business layer. The application and business layer is used to develop software applications with which the end user can monitor the general conditions of the crop. This is where the complete IoT solution is developed and integrated. This layer can be understood as the convergence between IoT and the grower. To carry out the development of applications that can use data generated, sent and stored in the previous layers, a web service will be available for developers. Application and business layer. The application and business layer is used to develop software applications with which the end user can monitor the general conditions of the crop. This is where the complete IoT solution is developed and integrated. This layer can be understood as the convergence between IoT and the grower. To carry out the development of applications that can use the data generated, sent and stored in the previous layers, a web service will be available for developers. Sensors and data transmitter module instrumentation. The instrumentation allows monitoring dozens square meters of the greenhouse area, which can cover a dozen plants. The greenhouse sensors configuration that comprise 8 temperature sensors, 8 related humidity sensors vertically located using 2 separate lines, a non-contact infrared temperature sensor, a light sensor, and a soil moisture sensor. The sensor's information transmission is by a module via category 6.8 wire-shielded cable. An Arduino microcontroller module receives and digitalizes the measurements. The ESP8266 transmits the information via Wi-Fi. Result: the experiment was conducted in a greenhouse with a mesh cover. In order to analyze the results obtained, it has been divided into two sections. The first is an architecture for monitoring environmental variables of the crop and soil, and the second is the validation of the data obtained. The architecture for monitoring environmental, crop and soil variables was designed, developed and implemented at a relatively low cost and easy to implement so that small producers have access to emerging technologies in order to be more competitive in the productive sector by developing sustainable production. Conclusion and field work. Taking advantage of the opportunity offered by the combination of low-cost hardware tools and free software, the design, implementation, and deployment of a low-cost architecture supported by IoT has been achieved. It has 4 layers of perception layer, network layer, store layer, and application and business layer. As further work, it is contemplated to expand the operation of the model so that it can make intelligent decisions based on the data obtained using artificial intelligence techniques. The implementation of this architecture in the first instance is intended to serve as a reference for researchers from different disciplines to implement it, since they are easy to implement and low-cost architectures. In comparison with the architectures that exist in the market, our proposal has the following advantages. The components are relatively easy to obtain and assemble. The cost of the sensor, microcontroller, and data transmitter are affordable for the small producer. It has an internet connection for sending data to the cloud. It is easy to implement. Its components are very light and compact with a weight of less than 1 kilogram, and the total cost of implementation is approximately $500. Acknowledgements. The authors would like to thank PRODEVSEP, CENIDET SEA 18-2020 project, and CONACYT for the support of the doctoral scholarship. These are some of the references. Thanks for your attention.